Section 10.3, question P26, manufacturing glass for the airplane windows and looking at their strength. So we have a sample of 31 measurements shown right here and plotted down here. These numbers are measurements of their strength, as we can see here on the label of that axis right there. And what we want to know, first of all, do the measurements look like they meet the conditions for testing the population mean? In other words, are we taking a sample of the right thing if we want to test the population mean? And yeah, I mean, we're looking at each of these measurements is a measure of the strength. The mean of these measurements should give us the average strength. So testing for the population mean, this is a reasonable set of data. So suppose the operation standard has 32 KSI for the process mean. Is there any evidence that the process is not meeting that standard? Well, we would take these, get an average, which we have right here, 30.81. Standard deviation, so this is a sample standard deviation, or should be anyway. Taking the SE mean. So what is this? This is the standard error. If we take 7.25, let's do that real quick, 7.25 and divide it by the square root of our sample size, 31, right there, you can see we get that 1.30. So this is our standard error of the mean. And because we're doing a one-sided test, essentially what we're doing now is saying that we don't care if we're above the mean standard. That would be perfectly fine with the standards board or whatever. The problem would be if we're lower than. So that's the only kind of test we're going to do. We're going to test versus this one-sided alternative hypothesis, which is why we just see a less than here, not a less than or greater than. And so this is what 95% is kind of like creating a confidence interval, except the entire remaining 5% is all concentrated towards the bottom here. So we'd have a t-value of negative 0.91. Again, that would just be using the formula, using the mean 30.81 minus 32 divided by our 1.3. And then we'd calculate a p-value 0.18. So for a 0.05 cutoff level, that's going to be above. In other words, we're going to keep the null hypothesis. We're going to fail to reject the null hypothesis. And so we're saying, hey, there's no real good evidence that we're not meeting the standard. Notice that doesn't mean that we're meeting the standard. It just means we don't have good evidence to say we're not meeting the standard. And this is tricky because this is really important, especially because it's tied to our sample size. The smaller the sample size, the less likely we are to reject the null hypothesis. So in a case like here, where it would be dangerous to fail to reject the null if it truly should be rejected, having a low sample size can really hurt us. Whereas if we're trying to show that some educational treatment is effective and we're failing to reject the null, that's not as big of an issue. The bigger error there would be saying that it works when it doesn't. But here, we do not have enough evidence to reject the null. In other words, there is no evidence, not enough evidence, that the process is not meeting the standard. However, if it was a higher standard, let's say 35, and we were testing a one-sided alternative hypothesis of less than 35, notice we still have all the same data points here and the same sample mean, standard deviation. None of that's changed. The only thing that's changed is our standards itself. And so here, when we calculate the t-value, this is going to be quite a bit different, because keep in mind that null hypothesis is part of the formula. We want to see how far apart this null and what we actually got in our sample is. So if this is higher, certainly there's going to be greater distance, and our t-value is going to be further away from 0. This gives us a p-value of 0.002, which is less than 0.05. So here we do have some reason to believe that the process is not meeting the standard. Okay, so notice with our mean of 30.81, even though we were below the industry standard, because there was this room for error, basically, because we're taking a sample, not looking at the entire population, we still didn't have reason to conclude that we were significantly below, or that the population was not 32 of ours. So even though we were below, we didn't have enough evidence to say that it was significantly below. Whereas this one, same thing, we were below, but we were far enough below that we could say, yes, this is statistically significantly below.